All right, the final unit in this chapter is on what's called the complex plane. And the first thing I have up here is that a complex number in standard form can be written as z equals a plus bi. So just thinking in terms of what a complex number is. A complex number is a sum of a real part plus or minus an imaginary part. We've seen complex numbers before, so 5 minus 3i would be a complex number. Now, we know from back in grade school that to graph a whole number like this, or a real number, we just find where it is on the number line and we put that point. Now, how on earth do we graph a complex number? Well, we can graph a complex number on a set of axes. Now, it's not an xy axis, it's a real axis and an imaginary axis. So 5 minus 3i would be 5 units in the real direction and minus 3 units in the imaginary direction. So here would be the point 5 minus 3i. Now, from way back when we learned that the absolute value of 5, this means the distance at this point is away from 0. Well, that distance is 5. In this case, the absolute value of 5 minus 3i, it means the distance this point is from the origin. So we'd have to find this distance right here. Well, to find that distance, we can make a right triangle out of this and use the Pythagorean Theorem. So that distance would be 5 squared plus negative 3 squared, and then the square root of that. So the absolute value of 5 minus 3i would be the square root of 34. So careful, absolute value does not mean make everything positive. Careful. It means distance from 0. So if you plot this point, how far is it from the origin, or how far is it from 0? Okay, now that we've got that down, let's go into an example of dealing with these complex numbers. Now, we saw these kind of problems back earlier in the year. So to add two complex numbers, we can add the real part and the imaginary part. There's your whole answer. We're totally done. We know that to subtract two complex numbers, we subtract the real part and subtract the imaginary part. And I hope you agree that these problems are relatively easy. To multiply complex numbers, here it gets a little tougher. Here's where we have to use the distributive property, multiply each of these terms together. So if we multiply the first couple terms, the outer terms, the inner terms, and the last terms, and then remember I squared is negative 1, so then we can combine some like terms together. Oops, let me get rid of that. So we have 10 plus 21, and then putting this together. So a little bit more difficult than those problems above, but still not too bad. We saw these problems before. Now to simplify this, we have to multiply the top and bottom by what's called the conjugate of the bottom. So multiply top and bottom by 2 plus 7i. And I think you'll agree these are more complex. They're doable. We did these first semester. I won't run through all this. I'll just put dot, dot, dot here because these are getting a little bit more complex. What about this one here, 5 minus 3i to the 10th power? Now, what we can't do is just take the 10th power of everything. What we have to do is multiply this out 10 times and then continue to multiply this over and over again. And I think you'll agree that this does not sound like a good time. This would take us a good part of the day to take care of this, and we'd probably make a mistake somewhere along the way. So one thing we're going to learn today is how can we do problems like this and this easier by rewriting these complex numbers in a different form. Okay, so here's that other form. So instead of the standard form, we can write trigonometric numbers in what's called trigonometric or polar form. So this polar form is what we're looking for. So these trigonometric numbers can be written in the form r, where r stands for radius, or distance from 0, times the cosine of theta plus I times the sine of theta. Theta is the direction angle. R is the magnitude. So we can see here r can be found by using the Pythagorean Theorem. There's your magnitude. Theta can be found by using tangent. And then each of these dimensions up here can be found by using sine and cosine. Now, sometimes people are told to memorize these formulas. I would say never ever memorize these formulas. Instead, let's just think of an example. Let's think of this complex number as being, oh, I don't know, let's say 5 plus 3i. If we sketch this, it's 5 to the right, 3 up. Yikes, that's the worst right triangle I've ever drawn. We can find this angle here by using tangent. Tangent of theta equals 3 over 5. We could find this dimension here by using the Pythagorean Theorem. 5 squared plus 3 squared equals this dimension here, which would be the square root of 34. If you were looking for this distance here, you could use cosine to find it. If you're looking for this distance, you could use sine. That's these two right here. So these formulas look complex. They're really just trigonometry. We know all of these. Do not memorize these. Instead, sketch a right triangle, even an ugly right triangle like I did, and use what we know about trigonometry. Okay, so let's take a look at an example. Find the trigonometric or polar form of this complex number. So let's start by sketching this. So this complex number means 2 units to the right, 2 units up. There's where the graph of this would be. I'm going to make a right triangle out of this. So this is 2 to the right, 2 up. Now, trigonometric form looks like this. So a complex number is r times the cosine of theta plus I times the sine of theta. It looks really complex, right? It looks really difficult. R is just this magnitude. I'm going to label that R. Theta is just this direction angle. So let's use the Pythagorean Theorem to find R. So R is equal to 2 squared plus another 2 squared, those side squared, and the square root of that. So that's going to be the square root of 4 plus 4, or the square root of 8, which you can write as 2 times the square root of 2. So I'm going to plug that in this spot. Theta is this angle here, so using SOHCAHTOA, I can say the tangent of theta equals opposite over adjacent. And if we take the inverse tangent of both sides, you'll find that theta equals 45 degrees. So let's plug that in. And that's your final answer. So using some trigonometry, you can find R, which is this length here. You can find theta, which is this angle here. Plug those in, and you're done. That wasn't so bad, was it? I didn't think so. Okay. So let's go the other way now. Now it's a complex number. Let's write it in standard form. So let me draw it first. So I'll put a set of axes. This means the point that's 4 units from the origin at an angle of 60 degrees. So at 60 degrees, I've got a point 4 units away. There's that point. Now again, we could use formulas here, but I could just think, hey, I need to know this distance here. I'm going to call it x. I need to know this distance. I'm going to call it y. Don't try to find both of them at the same time. Let's find one at a time. To find x, we can say the cosine of 60 degrees equals x over 4. And if you multiply 4 times cosine of 60, you'll get x equals 2. Likewise, we could say the sine of 60 degrees equals y over 4. And if we multiply both sides by 4, use our calculator, we get y is about 3.5. So in standard form, this number is going to be, I'll say this complex number is equal to, we took 2 steps in the real direction plus 3.5 steps in the imaginary direction. So there's this complex number in standard form. So the past 2 examples here, we started in standard form. We wrote it in polar form. Here we started in polar form. We wrote it in standard form. So we should be able to go both ways with that. Okay, so I'm going to get back to that original problem. Remember when we had this and I said, okay, multiplying these is not so bad. Dividing these is kind of a pain. There's an easier way to do this. if instead of these standard forms, we had this written in polar form or trigonometric form, this is much easier to work with. So let's say you have some number in, and actually this is two complex numbers in polar form. To multiply these together, pretty easy to do. You multiply what's on the outside, and you add the angles. To divide these, we divide what's on the outside and subtract the angles. Now again, these formulas look really complex, but if we look at a couple examples, they're not bad. So this fourth example says, let's multiply these two complex numbers together. Okay, to multiply them, what we do is we multiply what's on the outside. So we get 16. Hey, that's pretty easy. Times the cosine of some angle. What's the angle? Well, the angle we get by adding these two angles together. Yikes, that could be kind of a mess. So to add these, I'm just going to go over here, do some work. I'm going to get some common denominators. 4 pi over 6 plus 11 pi over 6. That gives me 15 pi over 6, which if I simplify, divide both by 3, I get 5 pi over 2. Okay, so 16 times the cosine of 5 pi over 2 plus I times the sine of 5 pi over 2. There's your entire answer. We're totally done. Hey, that's not so bad, is it? No, not at all. Now, one warning for you. 5 pi over 2, if you think about where that is on the unit circle, here's 1 over 2, 2 over 2, 3 over 2, 4 over 2. 5 pi over 2 is right here. It's the same place as pi over 2. Now, if you leave your answer this way, it's fine. But if you look up an answer like in the back of the book, you'd probably see that it's written in this form. Does it have to be written in this form? No. But just realize that it can be written in this form. Okay, let's look at a division problem. So to divide these complex numbers, we can simply divide what's on the outside, 3, times, and subtract the angles. The cosine of 225 degrees plus I times the sine of 225 degrees. And that's it. We're done. So remember, I'm going to flip back a little bit. I'm going to flip all the way back to something we started with. Remember, multiplying and dividing these kind of a pain if they're in standard form. Multiplying and dividing these complex numbers pretty easy if they're in trigonometric form. Oh no, I almost missed something in the directions. It says, write the answer in trigonometric and standard form. Standard form is pretty easy. Let's just distribute this 3 by everything on the inside. 3 times the cosine of 225, you can plug that right in your calculator. 3 times that's going to be negative 2.1. And then plus, do the same thing. Hey, we also get negative 2.1 times I. So once you get in this trigonometric form, distribute the 3 throughout, type it in your calculator, there's your answer. Piece of cake. All right. Now, what if we had this? What if I asked you to square this complex number? Well, square means times itself, so I'm just going to write this out again. Cosine of theta, r cosine of theta plus I sine of theta. Now, we know to multiply these, we can multiply what's on the outside, so r times r, and add those angles together. So let's say the cosine of 2 theta plus I times the sine of 2 theta. Now, let's just think about this. If we would keep going with this, if I, instead of z squared, I asked you to find z to the 3rd, you'd have another r, and you'd have another theta to add. Now that leads to, what if I asked you to find a complex number to any power? Well, that would be the number on the outside to that power times the cosine of whatever that power is times theta plus I times the sine of whatever that power is times theta. Ooh, that's going to lead into a big theorem. This is what's called de Moivre's theorem. Now, if you recall, taking a complex number to a power is very, very, very difficult. However, if it's in this polar or trigonometric form, it's actually relatively easy. Let's look at one last example. So if I want to find this to the 12th power, here's the hard way to do it. Hard way is to multiply this out 12 times, etc., etc. Multiply using the distributive property. Oh my goodness, it's already not looking too fun, so I'm going to get rid of all that business. And let's do it a little bit differently. Let's instead convert this into trigonometric form and then use de Moivre's theorem. Well, to convert this, I'm just going to make a sketch. This means 1 unit left and square root of 3 units up, which is about up here. So here's what this looks like. Here's where this point is. We need to know two things to convert this to trigonometric form. We need to know r, and we need to know theta. So I can say, okay, to find r, I'm going to use the Pythagorean Theorem. -1 squared plus square root of 3 squared, and the square root of that. So I get r equals the square root of 4, which is 2. Okay, there's my radius, 2. It's 2 units away from the origin. To find theta, I can say the tangent of theta equals opposite over adjacent. And then using my calculator, I can use inverse tangent to find theta must be equal to 120 degrees. So this point can be written as 2 times the cosine of 120 degrees plus I times the sine of 120 degrees. So that's the difficult part, writing this standard form in complex form. Now we want to take this complex number, in polar form or trigonometric form to the 12th power. Well, de Moivre's theorem tells me that this is pretty easy. It means take that initial number to the 12th power. Then take the cosine of 120 times 12, which is 1440 degrees, plus I times the sine of 120 times 12, or 1440 degrees. And there's your answer. Well, let's clean things up a little bit. 2 to the 12th I know is 4096 times what's in parentheses. Now, I'm not even going to bother to simplify these, because I'm going to let my calculator do the work. I'm going to distribute what's on the outside by everything on the inside. Well, if I do that, this turns out to be 1, so I get 4096. If I do it a second time, this turns out to be 0, so 4096 is my entire answer. It's kind of hard to believe. If I would have written this out 12 times and multiplied all these different terms together, this is what I'd get in the end. Well, in reality, I probably wouldn't get that because I'd make mistakes along the way. So converting to polar or trigonometric form and then using de Moivre's theorem, much, much easier. Okay, we definitely need some practice on this. So check out some problems on page 456. Once you're set with this, you are done with this unit.